We will now go through the process of hypothesis testing for a population mean when the population standard deviation sigma is known. And in this lecture 9C, we will examine the case for a one-tailed test. There are two approaches to solving a hypothesis test. The first using the p-value and the second using the critical value. The p-value is the probability using our test statistic, in this case based on the z-distribution, using our test statistic to measure the support for the null hypothesis. If the p-value is less than or equal to the level of significance alpha, the value of the test statistic is in the reject region, and we will reject the null hypothesis. Even without knowing the level of significance alpha, there are some simple guidelines for interpreting the p-value. A p-value less than 0.01 means there's overwhelming evidence to reject the null hypothesis and conclude that the alternative hypothesis is true. But a greater than 0.1 p-value says there's not enough evidence to conclude that the alternative hypothesis is true. Therefore, we do not reject the null hypothesis. This diagram describes a one-tailed lower tail hypothesis test for the population mean, where we know the population standard deviation sigma. In this case, we would calculate a critical z-value of 1.28 given a significance level of 0.10. Note, with a one-tailed test, all of the error is in one tail. So for that significance level of 0.1 and a critical z-value of minus 1.28, we have calculated a test z of minus 1.46. This gives us a p-value, a corresponding probability for that z-value of 0.072. Since that p-value is less than alpha, we reject the null hypothesis. In all cases, if our test shows the result to be further into the tail of the distribution than our critical z-value or significance level, then we reject the null hypothesis. A similar example is here for a one-tailed upper tail test. And again, we see for a significance level of 0.04, in this test we calculated a test z of 2.29. Its equivalent probability or p-value to the right of that is 0.011. This is less than the significance level, so again we would reject the null hypothesis. The second method of hypothesis testing is the critical value approach, and this may be a little bit more intuitive to most. In this case, we calculate a test statistic, in this case a z-value, given our sample mean. We then calculate a critical z-value, which is equivalent to the tail of the distribution for our significance level alpha. And we will reject the null hypothesis if our z-test value is less than or equal to the negative z alpha or greater than or equal to the positive z alpha. So an example of the reject criteria for a lower tail test is shown in this diagram. We calculate a z-test value using the sample mean minus the hypothesized population mean divided by the standard error of the mean, which is sigma over the square root of n. For that calculated test statistic, we then determine or compare it with the significance level z-value, z of alpha, as minus 1.28. In this case, if our test z is further left into the tail of the distribution than our critical z-value, we reject the null hypothesis. Similarly, for an upper-tailed one-tailed test, we calculate a z alpha, or our critical z, to be 1.645. If we end up with a z test value which is greater than that, in other words, further into the tail of the distribution, then we will reject the null hypothesis. It's convenient to follow a 5-step process for hypothesis testing, whether we're doing the p-value approach or the critical value approach. Obviously, the first step, develop the hypotheses. The second is determine the level of significance alpha. The third is collect the data and compute the value of the test statistic. For the p-value approach, we will use that z-test value to compute a probability or a p-value. And finally, we will compare that p-value to the significance level. For the critical value approach, steps 4 and 5 change. We use the level of significance to determine the critical value, and then we compare the test statistic, our z-test, to that critical z and determine whether to reject the null hypothesis. It's important to go through an example. In this case, we are given the sample mean of 13.25 and a population standard deviation of 3.2. We want to test with a 0.05 level of significance, in other words, a 95% confidence level, to determine whether the service goal of 12 minutes or less is being achieved. Now, as I read this situation, I'm told about a goal less than or equal to 12 minutes, which would imply that this would be the null hypothesis. Following the process, first define the null and alternative hypotheses. The null hypothesis is the population mean is less than or equal to 12, and the alternative is it's greater than 12. This implies a one-tailed upper tail test. One hint, as you look at the direction of the inequality in the alternative hypothesis, it's pointing to the right, which implies an upper tail test. And we specify the level of significance as alpha is 0.05. Using that, we will compute the value of the test statistic, and that is the sample mean minus our hypothesized population mean divided by the standard error of the mean, which is sigma over the square root of n. This gives us a z-test value of 2.47. Following the p-value approach, from that z-test of 2.47, from the z-distribution table, we come up with an area in the upper tail of 0.0068. Now, to definition, we would compare that 0.0068 to our significance level of 0.05, and we would reject the null hypothesis. Displaying that, we see that for a significance level of 0.05, we calculate a z statistic of 2.47. Its corresponding probability or p-value, 0.0068, implies that we reject the null hypothesis. If we follow the critical value approach, we determine the critical value for our significance level. So a z for 0.05 is equal to 1.645. And we would reject our null hypothesis if our z-test is greater than that. Well, we calculated a z-test of 2.47. It's greater than 1.645, so therefore we reject the null hypothesis.